Yeah, so let me introduce the speaker. This is Juergen from Astropeiler Stockert, and he will give a talk about the Astropeiler and give an introduction to it and tell what they do, interesting stuff for it. So welcome, Juergen Starek.
Oh, thanks, Stefan. Still a bit empty this morning, so I'm hoping that things will fill a bit up. Yeah, first of all, this is the telescope I'll be talking about for the next time, the Astropeiler on the Stockert mountain in the Eifel, right next to the small town of Bad Münstereifel. And yes, I'm just going to talk a bit about what we are doing there, what the background is, and hopefully give you a few interesting inspirations. So when I'm saying we, first of all, we should of course talk about who is this we. First of all, there is our club, the Astropeiler Stockert e.V., which has around 150 members, of which, if we are honest, perhaps 15 or 20 are really active only. That's completely a volunteer organization. We have no paid experts or anything. And the club was founded in 1995, was more or less inactive for around 10 years, and afterwards could go really deeply into the restoration and preparation of the telescope. But that is a project of a scope that you can't do alone, especially with a small team of volunteers. There are some challenges that are just too big, and the very nice and very interesting constellation that we're in is that the owner of the entire observatory is the NRW Stiftung. That is a public body that is responsible for all the monuments in the Bundesland of Nordrhein-Westfalen. And that means we have a very experienced sponsor at the back who's good at project management and who led us through some very difficult times. That was a really very important and cool partnership. Let's take a look a bit at the observatory itself, just so that we know what we're talking about and what infrastructure we've got there. This is an aerial photography of the site from the time of the construction. And we're seeing up here the 25-meter telescope, the oldest telescope on site, which is colloquially called the Astropeiler. That's actually a marketing term from the 1950s. They combined astronomy and Radiopeilung into something that the newspapers would print. The name just stuck. And later on, the observatory was augmented by this small, in quotes, 10-meter dish. The idea was mainly to provide a possibility to work on higher frequencies. And apart from the telescopes, we've got a laboratory building over here, and one, and unfortunately one is not visible, houses that were just there for the, well, technicians and guest scientists, whoever came around. As I said, the Astropeiler was built in 1956, of course at that time with a bit different means than you would today. And at that time it was a project that was also important for showing that in post-war Germany, science and technology were at a certain level again. The Allies had to lift their ban on German radar research only for this project so that it could be built. And a project of this scope, this is the final mounting of the dish in early 1956, was at that time only possible with some military usage as well. So over the years, the telescope was used, as I said, for military purposes. They did some basic radar testing, which, by the way, is also the reason that the telescope is put on top of a mountain, which is an incredibly stupid location for a radio telescope because you get all the wind and all the load from the wind pressure on the antenna. That in turn is the reason why our antenna has a wire mesh on the main surface and not a solid surface, which in turn has some drawbacks for us in electrical terms. I will come back to that later, just to tell a bit about this unusual place that they built it up. That was the military. Apart from that, and by the way, the military usage didn't last very long, it was of course used for fundamental research in astronomy, by both the University of Bonn and later on the Max Planck Institute for Radio Astronomy, which is co-located. But since Bonn is a very strong location for radio astronomy in Germany, it was also chosen as the location for Germany's 100-meter telescope, which was built in 1972 in the small town of Effelsberg. And of course, once you've got such a big instrument, the smaller ones get relegated to second-rate tasks. So Stockert was only there for tests, for smaller campaigns. It was used for students who did some exercises there. And finally, it had the very important task of being the place for the grill parties of MPEFR in Bonn. And at that point, the uni retreated completely, and everybody was thinking about, well, should we demolish that thing? People said, oh, well, that's quite tricky. The concrete is so hard, it's expensive, and whatever not. So in 1995, our club was founded, and our main goal at first, for the first 10 years, was to preserve the complete observatory, as complete as possible, and to prevent demolition. After a few years, we could make some arrangements. The telescope was marked as a national monument, as a landmark. And in 2007, we could start with a big renovation campaign. That was the time when, of course, the partnership with NRW Stiftung came in very handy and was very important. Because you can see that the entire telescope at that time had to be scaffolded. And that is, of course, something you don't do yourself anymore. So this is how it looked like in the beginning. The company used some very large girders here on the structure of the telescope itself, built a platform, and on top of that platform we had a 3-story high normal scaffolding like you would use on your house. And this made it possible for the first time since the construction of the telescope. Here's a more detailed view of all this steel up there, to actually access the metal structure. If you take a look at this picture, you see a bit hidden under here, a ring-like structure in the telescope. This ring is still made from steel. Everything inside this ring is made from steel. Fortunately for us, the rest of the mirror is aluminum, so we didn't have to renovate that. We could concentrate on the innards. And as I said, this was the first opportunity for us to really go there and look at these pieces that were inaccessible for 50 years. And of course, we did some preliminary testing from the ground to see what the situation was like. It all looked quite well. We took a look at things with binoculars and with long telephoto lenses. Only problem was, when you actually touched the stuff, you noticed that there was silver paint, but no metal behind it. So that was the state of some of the structures in the telescope, and we were lucky to have made this 2007 renovation date, because otherwise it would really have been too late for the entire structure. But apart from all this metal work, we also used this renovation campaign to do other things. First of all, we did a complete rebuilding of all the electrical systems inside the telescope. The only thing that remained was simple electrical lines to light bulbs and things like that. All the other things were completely rewired, and I will touch that in greater detail in a moment. And we did some energetic optimizations on the houses. In that case, the reason for this strange configuration was that we completely rebuilt that one house here. We were lucky to get a member exactly at the right time who is very skilled in doing these things, and so we could salvage this very badly damaged thing. For me personally, this was a point where I could say, okay, no matter how badly damaged the house is, there's always a chance of stripping it down to the bare walls, rebuilding it, and you get something very beautiful out of it. Okay, so let's get to the more technical aspects of the entire system and take a look inside the telescope at the different systems that we're using. I'll be using this original drawing of the scope to give you an idea where we are in the following slides. And let's first take a look at the control systems which are in the first floor. So this by the way, is ground level. Here's the entrance. The control system itself was completely built by us, and again, we were very lucky to get a very skilled member at just the right time. Before, we were all a bit intimidated by this project because we thought, yeah, well, we need to move 90 tons here. Nothing may ever go wrong because it's one of a kind, this instrument. You can not make any mistakes. You need a very reliable system. And luckily, this guy came along and said, oh, hey, I'm building big machines for a living, and that's a telescope. That's easy. It's only got 2 axes. I'll build you something. And what came out of it is a very simple drive system that is modeled after the original for manual control. Manual control of a telescope works with these 2 panels and is essentially just like driving, I'm always comparing it to driving a crane. You've got the brake control here, brake release, brake set. You've got the 2 white buttons that switch between a fast and a slow gear. And then you've just got the potentiometer that you can turn and regulate the speed of the thing. And up here, we've got the old salvaged position displays. So that's essentially it. That makes it possible to drive the telescope into any desired configuration. And that would, of course, already be enough if we would just be looking at bright point sources in the sky. So that would be a system that you might use for very simple observations. We actually only use it for maintenance, and the computer-controlled drive system that does the actual heavy lifting, that's something I'll cover just in a moment. Let's take a look at the back end of the control system. We are using a Siemens S5 PLC here. The reason for that is that we want 2 completely independent security circles. The control software in the computer is completely safe. It knows about the limits of the telescope and adheres to them. And then the control system tells the PLC control what to do, and that in turn, again, knows about all the limitations of the telescope and monitors them by way of different algorithms. This is also self-built. We used some of the old 19-inch racks that were lying around the telescope, just refurbished them, and put in this S5 system. The rest of this cabinet is just full with wires that transport status information back into the control room. We've got a lot of switches throughout the telescope that tell us about various boundary conditions. We monitor the current going into the electrical drives. And of course, we monitor position and use it to do a control loop, which I'll cover in just the next slide. These 4 identical racks up on top left are what we call the control amplifiers. They take the 0 to 10 volt voltage that comes out of the PLC and amplify it to something in the range between 0 and 100 volts. That goes down in the cellar, gets amplified again, and then goes up to the engines. The reason that we have 4 is just for redundancy. These are very old devices from the 70s that we're reusing, and we just want to be on the safe side if they ever do anything strange. Now, I mentioned that we are, of course, using a control loop to keep the telescope position. This is classical control theory. What we're doing here, we've got the control software here on the left that tells the PLC the desired position. As I said, this is amplified in the 4 amplifiers in the rack. Then it goes down in the cellar to the amplidune. This is an electromechanical device, and its output goes up to the drive motors. Then the telescope has sensors. First of all, on the drive motors, you count how many revolutions they do. Then we've got absolute position sensors in the telescope itself, and that's the first line of defense against anything going strange. If you notice a motor spinning very quickly, but the telescope standing still, you're having a bad problem and should ideally stop the engines right now and apply the brakes. If nothing goes wrong, the position is read out by incremental sensors. That in turn is digitized by a small AD card in the control PC, and the information is fed back into the control software. That is a classical loop, and if you parameterize it correctly, you can compensate wind bursts rather quickly. That is a large problem with such a large dish on top of your building. The slightest burst of wind will turn it, will make it wobble, and this is something that needs to be compensated rather quickly. The control software itself is built like this. This is, by the way, a rather classical way of building astronomical control software. So if you're ever thinking about doing a telescope control system for optical photography or whatever, this would be a good way to do it. The user interface accesses either a list of targets, or you can enter the desired coordinates directly, or you can configure different scans across the sky. At this point, I should perhaps explain why it's so important for us to be able to scan. From optical astronomy, you know the concept that you access one point in the sky and you track it very precisely. In radio astronomy, we are more concerned with large area sources, especially cold gases in the galaxy. And in that case, the area of the source is normally so large that it warrants a cross scan. So you've got this source, you want to scan across it while that source is moving across the sky and showing an apparent rotation. So of course, the resulting pattern is something like, I scan like this and go over here and go over here, and you know that is something you don't drive by hand anymore. So we can parameterize these scans in the UI. Then the system knows the desired coordinates and the desired path that it will need to take. The coordinates are, if necessary, converted from any coordinate system. You enter them into our machine coordinates. Then the desired azimuth and elevation are calculated from out of that. Afterwards, we can apply corrections. That is very important because we don't calibrate our telescope anymore. Normally, for example, you would calibrate the instrument so that the azimuth axis is exactly vertical. This is a bit tricky, and we are preferring at the moment to do some so-called pointing measures. That means before we measure anything proper, we check the positions of known point sources in the sky. The computer makes an error model out of that, and we apply this error model to our desired observation. So any mistakes that are in the positioning of the telescope or in the alignment of the telescope get removed automatically, and we just calculate them out. Then comes the position control loop that I've just discussed. Information goes to the PLC, gets amplified, gets out to the drive motors. So that's essentially it for the control system, which happens down here, as I said. Next step, I've already mentioned it, is how do we get the power to the engines? We are using a so-called amplidune that is standing in the cellar. An amplidune is the marketing name for a so-called Leonard set, and that is an electromechanical power amplifier built in World War II areas for battleships, because at that time you had the problem that you needed to turn these huge gun turrets, which are extremely heavy, of course, and driven by electrical motors. But it was not possible at the time to amplify current via transistors or anything similar. So what you did was take a strong, big electromotor, couple it with two generators on one axis, and let that thing spin at a constant velocity. And by altering the current that goes into the generators, you can alter their output directly proportionally. So that's a very simple way of amplifying large currents. We are still running this thing. Unfortunately, we've only got one. I'm a bit envious of the colleagues from Ventspils who've got 6. So if one breaks, they can just move the cables around. If ours breaks, then yeah, we'll have to go to the drawing board. But this is very robust technology, and everybody can repair it essentially. So we are keeping it for now. And we're actually quite happy with the fact that it doesn't cause interference. That's, of course, something very important if you're running a radio telescope. Okay, so this was the control amplidune loop. Now, of course, the electricity goes up to the drives. We have 2 sets of drives. One here in the top of the pyramid, one up in the steel structure of the telescope. This entire part that is drawn like a vertical mast here in the middle, this is the entire part that moves. it is hanging essentially freely in the telescope. There is a ball bearing up here that takes all the static loads, and the rest is, as I said, hanging freely so that you can calibrate it. And if you look at the drives, it's big iron essentially. So that is what they built in the 1950s when you're thinking, for example, of harbor cranes or something like that. We're actually using very small motors on top of that. Then there's the 2-speed gearbox. In here there's the brakes, and then we're going to the proper large drives. There's an image of one of the cog wheels, and we're using such a large transmission ratio that actually at one point we bent our own security system. We've got these large U-girders where you can screw the telescope in place. And it was surprising how lightly you can bend such big steel rods when you've got a 1 to 1440 transmission in front. That was, lesson learned. We're not doing that again. Okay, those were the drives. But of course, just moving the telescope, I mean, that was a nice success in 2009. But in the end, what you want to do is measure things. So let's take a look at what we call the receiver front end. Let's take a look at the receiver itself. Our current front end has been built by professional partners. The Afghan wanted to use our telescope as a secondary receiver for their space debris radar program, very similar to what the colleagues from Ventspils showed us yesterday. Afghan is sending an active signal into low Earth orbit, waiting for it to be scattered off space debris, so old satellites, parts of screws that went missing, whatever. And they want us to be a secondary receiver for that. The aim is to make an accurate map of all the space debris that is floating around there, because that's a huge problem for commercial space ventures today. You need to know where these things are. And if you follow the tracks of the ISS, you will notice how often they have to boost their orbit by a few kilometers just to evade space debris. That happens once a week, roughly. So this is a really very important thing currently. Because they wanted to do that, the receiver itself has a design frequency of 1.3 gigahertz, which is their radar frequency. And it is also usable on 1.4 and 1.6 gigahertz, which are very important astronomical frequencies for us. Looking inside such a receiver, it's a very simple design. They're just building an aluminum box. We've specified a standard size for these boxes because we wanted to be able to exchange receivers. And inside that box, you see a smaller box that contains all the electronics. And the round rod that is extending to the right is actually the receiving horn. It ends in a so-called, pity, I just forgot the English term for it, a so-called Rillenhorn in German. And that is a very flat sort of horn. You don't need such a large construction anymore, and works purely by interference between waves. I'll show you a detail in a minute. The entire box with the horn is movable on the image from left to right. Of course, if it's mounted, it's the z-axis, so it's the distance between receiving horn and antenna. And that is essentially our focusing mechanism. Occasionally, you want to do defocused measurements because defocusing means your receiving beam gets wider, you lose sensitivity, but you can look at larger areas at one time. Inside, the electronics are, again, standard issue, essentially. This is an image of the intermediate, I wrote ZF, sorry, in English that should be IF, of the IF boxes in the front end. Very classical engineering. I won't go into too much detail here because that's also not really self-built. The blockchain is more interesting because what they are doing here is very straightforward HF amplification and design. You come in here from the receiving horn, and the first thing is a so-called orthomode transducer. An orthomode transducer separates wavefronts with different polarizations. So you've got a round horn in front, and the orthomode will send a wave that's coming in this polarization to one side, and a wave that's coming in that polarization to the other. Side in that case means one of two identical receiving chains. So you've got an amplifier in front, you've got a bandpass filter that rejects unwanted signals, and then you're going rather directly to the mixer. We're sending up intermediate frequency of around 1,200 megahertz upwards to the receiver. So that means after the mixer, our intermediate frequency is in the area of 170 to 200 megahertz. And these are frequencies that you can handle very well on a normal coaxial cable. You don't want to send even an amplified signal with 1.4 gigahertz over coax cable. It would just incur too much losses. So what we're doing is convert this down to 170 and send this down to the receiving room. Now, of course, after a while working with that thing, we felt like, okay, it's very nice, we know what happens, works very well, but it would be interesting to get more frequency coverage. So a member reconfigured a satellite receiver, a normal satellite LNB, to be used as a 4 gigahertz front end. We're just mounting this at the moment in a piggyback configuration right next to the main receiving horn. By the way, this gives you a nice view of this so-called Rillenhorn. That's a bit of a tricky configuration to design and calculate, but the advantage is, of course, it's very easy to fabricate compared to the classical long tubes that you would require in such a situation. Yeah, so that's what we're currently having in the front end. And of course, we're sending the signals received by the front end down to the control room again. So the last step in the loop is, of course, we need somehow to make sense of what's coming down. And this is a surprisingly tricky task, but also a very interesting thing. We're using, well, what you in radio astronomy call backends to, first of all, take the intermediate frequency and digitize it somehow. We've got an FPGA-based spectrometer that has been designed for Max Planck Institute in Bonn, so that's also in use at the Effelsberg facility. We're just using it in a smaller configuration with just 2 FPGAs. And you can load different so-called FPGA cores into the machine to make it behave differently. We're using one core, the so-called continuum core, to use it as a classical spectrum analyzer, which is highly configurable and very capable. And for me, as an IT person, what I like most about this machine is that the FPGA itself does not only do the analysis, but it also generates a high-frequency signal that is sent out to a specific port and looks to the rest of the world like an Ethernet packet. So I can just plug in a small switch at the back of that system and get the measurement data out, nicely packaged in Ethernet packets. It's not really Ethernet, so the transceiver would not understand collision signals, for example. But it's good enough that you can just plug in a gigabit connection and draw all the signals out from there. And yeah, the other core is the pulsar core, which works also as a spectrometer, but with very, very different configurations, and with a focus on speed. We will cover pulsar observations in greater detail later on. Then we've got the small so-called pocket backend down at the bottom. That's essentially just a high-frequency power meter, but very nicely configurable. And we're also working with classical, well, yeah, I mean, now I guess you can say classical software-defined receivers in the backend, so GNU Radio, USRP, things like that. Even the RTL SDR, the small TV USB dongles that you can hack and reconfigure, work great as a configurable backend for us. So that's, again, a view at the entire, a block-level view at the entire measurement chain, starting from the receiver here on the left in white. The intermediate frequencies go to an intermediate frequency distribution system that just splits them up for all the different instruments we want to attach to it. And then either we're doing continuum measurements with a pocket backend. In that case, we've got a small detector in front and use the pocket backend as a receiver. That we've got a connection to the control PC that adds the current position and data, and then we're just writing CSVs. Or we're using the FFTS and writing FITS files, which is an astronomy standard for measurement data, and that's essentially it. The interesting thing comes afterwards, but for that, we will need a bit of theory. I promise I won't go too deeply into that because we're not an astronomy conference or physics conference here, but just enough that we understand what's going on. Radio astronomy itself was something that was theorized about after Maxwell's equations became public, and it was clear that all sorts of radiation were essentially the same phenomenon. So people were wondering, why are stars and why are galactic bodies emitting light, but why shouldn't they emit on other frequencies? In 1930, the phenomenon was accidentally discovered by Carl Jansky, who was originally charged with diagnosing problems in a transatlantic radio link. And he noticed a disturbance that came at the same time, almost the same time every day, only 4 minutes shifted. And if something comes up every day in 23-hour, 56-minute increments, you might think of, hey, that's essentially galactic time, right? That's or sidereal time. So in the end, it turned out what he measured was the core of the Milky Way. That was something that was received, well, it was received by the astronomical community, but there was no great enthusiasm. So in 1937, Grote Reber, a Dutchman, built a 9-meter telescope in his own backyard and created the first map of the Milky Way. And people began to suspect that there might be something interesting behind that after all. Then, of course, the war came, and science was essentially ground to a standstill. After the war, however, all of Europe was littered with these big German Würzburg-Riese radar dishes, and they were used by the radio astronomy community at that time as the first telescopes. In these times, you would just use a radiometer as a backend. A radiometer, as I said, is just a high-frequency power meter. And the simplest power meter you can imagine is just a bandpass filter. You want to reject all the interference that you're not interested in. Square law detector, so you can measure the power that's coming in as a proportional voltage, and a signal averager so that you're not disturbed by the rapid fluctuations. So that looks a bit like this. And that's actually it. You can do, well, not the most interesting, but you can do radio astronomy with such a simple setup, and that's something one can easily build themselves. In truth, however, you will have one problem, and that is that all diodes and all transistors are highly temperature dependent, of course. So if the temperature in your receiver case is fluctuating, the output of your detector will fluctuate as well. So what you're doing in practice is use a so-called dicke radiometer. You're using two feed horns. One is looking at the sky, and one is looking at a cold place, for example, the bottom of your antenna or something like that, or a calibrated noise source would be preferential. And you just switch between them. The rest of the design is just the simple power meter that we've just seen right now. But you're switching between them, and that means that if both signals you're getting are fluctuating at once, you're seeing a temperature fluctuation. If only the galactic signal is fluctuating, then you know that your local temperature is constant, and the galactic signal is actually fluctuating. So in this simple case, a radio astronomical measurement is just, I'm always saying, write 4 things on a piece of paper. Time, when am I measuring this? Azimuth, elevation, so the position of the telescope, and the energy that's coming in. That's essentially it. And you can do very patient measurements like this. You can step your position down 1/2 of a degree at a time, and that gives you a nice radio map telling you where to look for more interesting things. More interesting things in that case, for example, means you can take spectra of the signal that's coming in, because frankly, while there are very strong, narrow line emissions in the cosmos, it's a bit boring to only look for these lines. You can get far more information out of the sky if you can take spectra. This is an image from 1958, one of the first spectra that was taken at Stockert University. That's a position somewhere in the Milky Way. Nothing too special to see there. The interesting thing is just that at that time you had to use so-called switched filter banks for taking spectra. The thing is, you had a huge cabinet full of very finely tuned frequency filters that were just spaced something like 10 or 20 kilohertz apart. You would do your measurement, switch to the next filter, do a measurement again, and all the time integrating for a minute or so. switch to the next filter again, and so on and so on. So looking at the time, I don't know if it's really visible on this sketch. It's not really, but this took ages. This took hours. And the nice thing today is that by using FPGAs and far better amplifiers, we can take spectra essentially immediately. And while it's convenient for you as an observer, it's very important if you want to do, if you want to show this astronomy to visitors. We can just do live measurements of the galaxy and show them to visitors now in real time, which is very convenient. So I said that it's far more interesting to take spectra. And of course the question is now, what can we see even? What is out there, and what mechanisms are there causing this radiation? The important thing when talking about galactic radio emissions is you need to keep in mind that it's radio, but it's not modulated. There is no information in the signal per se, like we would be used from a normal radio signal or Wi-Fi or whatever. It's just noise, with some exceptions. The main mechanisms that lie behind it are simple thermal emission, synchrotron radiation, what's called Bremsstrahlung, apparently even in English, and different absorption and emission mechanisms in gas clouds. So thermal radiation, here's an example of a simple azimuth scan of the moon drifting by our telescope, is really just that. Every hot body emits radiation. So the moon, not being perfectly cold like the sky background, emits something too. And that's the reason, by the way, why we want our trees not to grow too high, because even now with the trees at around 15 meters of height, we see a significant increase in the noise level when we're moving down to the horizon, because that means we are getting all the heat from the forest into the telescope, and that's really a problem for us today. But that's not really all that interesting. The most interesting thing perhaps you can do with thermal radiation is take over a set time a set of measurements of the moon and compare how the sun darkness line on the moon moves compared to the radiation pattern that you get back. That gives you very interesting insights about the energy transport inside of the moon. You're essentially getting a possibility of remote sensing the cooling down of areas when they get in the shade. This is something that was done at Stockert in the preparation of the Apollo missions by NASA. They wanted to find out something about the particularities of the moon's surface. Didn't really succeed, but nonetheless it makes for a nice experiment even today. Next mechanism is synchrotron radiation. Same mechanism we're relying on here at DESY for our photon science work. It's called synchrotron radiation because in the original days when you used synchrotrons as particle accelerators, people noticed that as soon as you bend charged particles in an accelerator around a corner in a magnetic field, they will radiate excess energy. If your particle flies such a curve, the radiation is perfectly tangential. So in the old days, that was of course a source of energy loss for the physicists, and they were rather annoyed with it. Nowadays, we're using this radiation to power our laser systems here. I hope we can get more details on Sunday at a tour of the DESY premises. In the astronomical case, the situation is just that if you've got a star with a strong magnetic field that is moving through an ionized gas cloud where you've got free charge carriers like electrons, you're getting exactly this radiation. A typical example is this measurement of Cassiopeia A, one of the strongest radiation sources or radio sources in the galaxy that we've done at Stockert. These are the remnants of an exploded star in the middle of a very beautiful, actually, nebula. Next mechanism is Bremsstrahlung, also called free radiation in English. This is a mechanism where free electrons scatter off ions. Again, we're looking at ionized gas clouds in the galaxy here. Regions where this happens are called H2 regions. They are very interesting in terms of star formation. I won't go into many more details here. It's just that I think it's already becoming clear that we are not so much concerned with visible phenomena here. I'm always talking about gas clouds and stuff. So that's also the reason why you want to do radio astronomy. Astronomers always want to cover as much frequency area as possible. And radio astronomy is on the lowest energy end of the spectrum and looking at essentially all these invisible phenomena that you would not notice with any other techniques. Last mechanism is, or are, transitions in hyperfine structures of neutral galactic hydrogen, where whenever I talk about this in front of a normal engineer group, the reaction is, what? Understandable. This is such an important mechanism that I'm going to open a new chapter for it. We are working, I've already mentioned this when I talked about the receiver, we are working on, especially on the 1420 megahertz hydrogen line. And this is the emission mechanism that's behind it. It's a so-called spin flip in neutral hydrogen. The hydrogen atom, consisting of or having only one electron, can either have the spins of the core and the electron aligned or reversed. That's what is signified with that small arrow here and here. The spin flip, the reversal of the spin direction of the electron, is actually not really possible. It's something that is called a forbidden transition in that case. Turns out that because we're in an area where quantum mechanical mechanisms come into play, it does happen, approximately every 11 gigayears, so every 11 million years. Nonetheless, this mechanism gives us one of the strongest radiation sources in the sky. Every time such an electron flips, it emits a tiny amount of energy at 1420 megahertz. And the reason that it's, despite this long half-life of 11 million years, such a strong radiation source is just that we are looking into along a very long line through a really large field of gas. So at some point in time, some electrons are always flipping. The advantage is, this is a mechanism that can look through galactic dust. You can see signals that are obscured otherwise. And that was actually a very prestigious discovery after it was predicted by Jan van der Hulst. It was detected by Juergen and Purcell in 1953, which, by the way, correlates to the construction of our telescope, because this discovery pushed the building of very many similar telescopes throughout the world in this time. Now, what can we see with this mechanism? Well, first of all, we're looking at a cold hydrogen source, in this case, in the galaxy. This is one of the first measurements we did at Stockert. And we did that, and we were extremely happy to see this because, well, at that point, you know, you've got the drive system renovated, you've got the building renovated, you've got all the receiver chains set up. And we were very happy to see this. But honestly, in the end, we thought, well, it's just a spike, right? So there must be something more. And actually, if you move the telescope just a few degrees away, it becomes interesting. We know from theoretical considerations that the hydrogen line is always exactly at 1420 megahertz. Now, when we look at this graph, here's the 0 point, we see that this peak is a bit off. Then there's a second peak, which is very much off, and a third smaller peak, which is further off still. The normal explanation for this, and accepted explanation for this, is that this is a Doppler shift. We are looking at clouds that are moving relative to us, and the distance from 0 gives us the relative velocity. That is why astronomers like to talk about frequency shifts in terms of kilometers per hour or per second. So this axis here is actually a delta F axis, but we've converted it immediately into delta V. The width of this band is also interesting because I've said that the H1 line is always exactly 1420 megahertz. So if the line is spread up, that can only mean that the electrons in that cloud are moving with different relative velocities to each other. Why would I want to know that? That's why. When you're looking at the sky with optical instruments, especially from the southern hemisphere, you get this beautiful view of the Milky Way. But we can't really tell what the structure of the galaxy is. It is quite possible that we were sitting in a closed elliptical galaxy. It is even possible to imagine from this image that you're sitting in a discus. Nowadays, with our current huge optical telescopes, we can do something about that problem. But the original, easier solution to the problem was to use radio astronomy and to create a lot of patient measurements across the galactical disk, always looking at either emission lines, like I've just shown, or absorption lines, like in that case, and try to figure out what gas clouds lie in that direction, what their relative velocities are. And then you've got to do a lot of corrections, and you can draw these maps of the Milky Way as a spiral galaxy like we know them today. So this is, of course, an artist's impression, but in that image, the arms of the Milky Way represent approximately what we know today. The absorption spectrum here, by the way, I've just got to talk very quickly about this mechanism. We've got a broad source somewhere here, right? We've got a very broad, flat spectrum peak here. And the narrow indentations in the spectrum range from cold hydrogen clouds that are just between our telescope and this source in the sky. They essentially take out the energy from the spectrum at exactly these areas, and you can also use them to get information about intermediate gas clouds. The problem with this moving thing is, of course, our sun and hence our observatory, sorry, are also moving. So what you need to do is something called local standard of rest correction. That is something that our control program also needs to incorporate. Since the Earth circles around the sun and the entire system around the center of the galaxy, and the Earth and the Moon around their common barycenter, so the center of common gravity, everything's always in motion. So every speed measurement you take in the cosmos always has huge problems associated with it. You need to calculate out all these things. There's a formula for that will bring you to a stable reference frame. And what we do in the end is just calculate the error that we're currently making, translate that into a frequency shift, and have the computer alter our local oscillator so that this frequency shift gets compensated. Otherwise, of course, if I'm looking at, say, the Wi-Fi beacon over there as a source, and the Earth is just coming around like this, I'm getting a far lower velocity than if the Earth is moving away from it. That's something that we have to keep in mind all the time. And then, as I said, you can just go through the galactic plane, take a lot of measurements, do these calculations at all the time, and you get a galactic map out of it. That is, by the way, something we want to do as a demonstration experiment for visitors, but one of the many things we just did not get around to doing yet. Next big topic we're working on is pulsars. And this is the one main area where you actually are looking at signals that are not continuous over time. A pulsar is not really well understood. There's a nice quote here from Michael Kramer and Duncan Lorimer, two of the leading people in the field, from 2005 still, where they say, well, in spite of almost 4 decades of intensive research on pulsars, is it a fair statement that pulsars are only understood poorly? The problem is we basically know what's happening. At the end of their lives, stars collapse, and due to conservation of momentum, the very small remainders, normally called neutron stars, spin extremely fast because they're carrying the rotational momentum of a star many hundreds of millions of kilometers, perhaps, or hundreds of thousands of kilometers in diameter, onto a very small sphere. If this sphere now has a magnetic field, shown here as these blue lines in the graphic, and rotates along an axis that is not aligned with the magnetic poles, then you've got a rotating magnetic field in perhaps a cloud of ionized gas, remind us from the explosion. And then you get this classical synchrotron radiation mechanism. Magnetic fields, electrical carriers, everything's in motion, everything radiates. And you can imagine now if you let the pulsar in this illustration rotate along the green axis, that these red radiation beams would occasionally pass by my desk here every second or every revolution. And this is essentially what we're seeing from pulsars. We are seeing very, very short spikes. And the interesting thing about pulsars is finding them. It's actually rather tricky. So what do we want to do on the sky? We want to find these very short spikes. So, okay, That means we have to record our signals with a very high time resolution. The problem is, I've just mentioned that the signals are very, very weak that we're getting in. So you would possibly not see anything because your receiver noise is too bad. So what can we do? We need to gather more energy, but we can't really integrate over a longer time. One possibility is to build bigger dishes. That ends at some point. Currently 100 meters for freely movable dishes, 300 meters for stationary dishes. The other thing that remains is we can widen the frequency range because pulsar emission is rather wideband. You can just look over a larger spectrum, integrate all the energy that you gather over that spectrum, and use that all together. But the problem is wide frequency ranges are problematic. First of all, you get man-made interference, which is today basically everywhere, right? Everything we use is based on rectangular signals. All the electronics are using rectangular signals. So every switching power supply, every screen creates a massive amount of disturbance for us. The other thing is the signal itself interacts with the interstellar medium in a way I'll just show in a second. So we need to apply quite some signal processing to it. This problem with the interstellar medium is the following. It's called dispersion. And if you've got plasma on the way that the signal takes from the pulsar to your telescope, the plasma actually slows down the radiation in a frequency-dependent manner. So in this FT graph I've sketched here, you see that individual frequencies, if they are sampled, are delayed by a small amount. That means that if I integrate over that stuff, in the end I will get a cancellation of all my frequencies because they are shifted so much. So we need to get rid of this dispersion effect. That's a process called de-dispersion. We want to individually sample all these frequency bands, move them according to the delay they experience in the interstellar medium, and add them up to nice, sharp, high peaks, because that's something we can work with. Well, almost. It's still a very, very weak signal. So even if you de-disperse a signal, the pulsar signal is buried in noise, and of course, you always want to push the frontier forward. You always want to detect fainter pulsars. So you need to be able to really look at these extremely weak signals. And now if you think of it, if you want to detect new pulsars, you don't know where to look. So you look at some point in the sky. Systematically, you just scan an area. So that's your first unknown. Then you don't know how far away the pulsar will be. So you don't know how much dispersion the signal will have. Third is, you don't know what the pulse rate of the pulsar will be, because you need the pulse rate for the final folding step. So that is why pulsar search is a canonical example for, in IT terms, for an O of n to the third algorithm that you can't optimize. You've got an O of n to the third algorithm that you just, well, you can parallelize it. There's a lot of trying stuff out. You can just build a large parallel computer for it. But there is no way of getting this problem optimized algorithmically. Here's a nice excerpt from a slide by Lorimer that shows the entire pulsar searching progress in an overview. This is what you get from the telescope. You measure at some point, you take spectra with a very high time resolution, so there's not so many frequency bands. And if you look at it, it's all noise. You can't really make any sense of it. So here's the first step. You try some dispersion measure, de-disperse the time series. It may look interesting, but actually this is still, from a statistical point of view, not really distinguishable from noise. So the next thing is you do an FFT to see a nice amplitude spectrum coming out. If it looks like this, great. That sounds interesting. We save it as a candidate. Perhaps we should try another dispersion measure. So this is one of the unknowns in this loop here. If you are satisfied with that dispersion measure, you can fold the candidates. Then you've got the second unknown, namely the pulse rate. So you need to fold with different parameters. And like he writes down here very nicely, once in a while you'll see a pulsar. This is, of course, something that has been highly automated today, and professional observatories are doing it. we are honestly keeping out of the searching business because our antenna is too small, our receiver is not cooled, so its noise figure is a bit too high, and we've got too much man-made interference. But what we do is look at known pulsars. That, by the way, makes it also a whole lot easier if you know the dispersion measure from literature, and look at at interesting phenomena that are happening. This is in the very nicely named pulsar B0329 plus 54, an interesting phenomenon called mode switching. If you look at these pulse profiles, you see that normally the pulsar has a tiny forepulse, then a very high main pulse, and a slightly lower afterpulse. First of all, what mechanism can cause this? This is actually something that is still debated, because imagine a small neutron star spinning in the way we've just described. What mechanism should cause this pre-pulse, main pulse, afterpulse pattern reliably every rotation? That's completely unknown. What's more unknown is, it's speculated upon, it's not really well understood. What's not known today is why this pattern shifts occasionally. These are just seldom, rare occasions, individual pulses, where the first pulse is higher than the afterpulse. This is something where we can actually contribute a bit, because these observations take a lot of time, and professional observatories are, of course, heavily oversubscribed. So this is something where we can offer observation time. Another interesting phenomenon is that, for example, the Crab pulsar, very well-known object, occasionally emits giant pulses, which are very much stronger than normal pulses. This is also not quite clear why this happens. We've tested it, and we can see it rather well. So this is, again, one thing where we would offer observation time to anybody interested. And to conclude this walkthrough through radio astronomy, we have also observed several other phenomena. Amongst them are radio recombination lines, which is a similar mechanism to the hyperfine transitions. We're seeing high-velocity clouds in the galaxy. These are gas clouds that do not adhere to the normal movement pattern of the galaxy at all. And it is not quite known why they are moving, in some cases even tangentially to the galaxy. As I said, we see them, we can map them. We have done a lot of work on OH masers in recent times. We're looking at active galactic nuclei in far away from our own galaxy, and we're taking even spectra of other galaxies. The example down here shows both effects at the same time. At the left, we see a very tiny spectrum of a high-velocity cloud. At the right, we see an extragalactic spectrum of a dwarf galaxy in somewhere in Ursa Major. And you can see that there is quite some work for us still to do to improve the signal quality. We see these signals, but in order to make them analyzable, we need to work on the amplification, we need to work on the back end and improve these things. Okay, moving away from radio astronomy, what else happens at Stockert? We are doing amateur radio quite a lot. We are working in fields of optical astronomy and, of course, doing a lot of stuff ourselves. The Stockert is a rather good place for optical astronomy. It's got a nice dark sky for Western Germany. And so we can offer visitors to telescopes, an 8-inch and an 11-inch. We've got some smaller ones, mostly donated, so that's quite enough for nice astrophotography. And we're always open for people who just want to use the place for that. We offer a laboratory and some workshops. In the electronics area, we can go up to a kilovolt in terms of power supplies. We can analyze high-frequency things, signals up to 18 gigahertz. And we've got the normal supplies like oscilloscopes, tube testers, whatever. And we've got very simple, basic metal and wood workshops just for the daily work out there. In the field of amateur radio, that has always been a core activity in our group, and of course, if you've got such an observatory, it attracts people who are themselves attracted to antennas. We are currently transitioning the shortwave station. There will be a shortwave station in a short time. We've got 4 11-element Yagis for 2-meter Earth-Moon-Earth traffic or moon-bounce traffic on azimuth elevation rotor. So that means we've got these 4 huge antennas being able to track the moon, and you can send your signal to the moon, get the reflection back, and thus reach the entire half of the Earth where the moon is currently visible in terms of amateur radio. We're also doing this on 10 gigahertz. The VHF thing is actually a very recent development. We've done this on 10 gigahertz for quite some time on the 10-meter dish. And we are one of, let's say, only 40 to 50 stations worldwide that can do this on 10 meter. As soon as you can get your hands on a dish, let's say about 6 meters in size, which is what gets thrown out of many satellite downlink stations currently, and you can get them very cheap, that is a very rewarding thing to do yourself. And the latest development, we're doing interferometry on 10 gigahertz as well. We are using 2 1.5 meter dishes built on top of the roof of the building. I'll just show you an image in a second. They are equipped with normal satellite LNBs that are just modified. Their quartz has been taken out, and a central LO clock source has been attached. And we're just wanting to see what's possible with that. It's actually been a Jugendforsch project, which is in Germany a program for students who want to do interesting things from the entire STEM field. As I said, the problem was the LOs in the LNBs were drifting, the local oscillators, so we had to attach a single clock source. Then we're getting, of course, interference from commercial satellites, but bandpass filter solves this. And then you need to throw a bit of signal processing at the problem. And one non-HF challenge was the students, of course, wanted to be able to steer or control this from their homes, so it was made remotely controllable. This is the setup. You can see, by the way, all the other antennas too. This is the 4 times 11 element Yagi group for 2 meters that I've just mentioned. Then these 2 light gray dishes on the top of the roof are the interferometer. The dark gray one is actually a satellite dish used as you would normally use it, just for TV. And in the back, we've got a mast of a private shortwave station carrying a large directional antenna, large quad, and some wired antennas. So what's this thing with radio interferometry? You've possibly talked to the LEGO optronics guys. In radio interferometry, what you want to do is work on the problem that radio telescopes in general have a very broad beam. You can't get fine images from them. So one trick that you can do is couple more antennas together in the classical interferometer configuration depicted on the left. And what changes, I've drawn a sketch of the antenna pattern on the right, is just the directional pattern of your general antenna system. The black line on the right is an example of a classical antenna pattern for a directional antenna, so you have to read this as gain over angle. So the gain is greatest in the direction right in front of you, and it gets smaller the further out you get. If you combine these antennas into an interferometer, you see that the pattern gets these small fringes, these narrow fringes. And if you know this pattern, you can, of course, calculate out the pattern of the measurement and get a very narrow beam, increasing your angular resolution. I've just got the very first interferometry data that we've taken here. That is, of course, not very processed yet, but we can very clearly see that even with these small 1.2 meter dishes, we can see the Orion Nebula drift through. And the next step is, of course, to attack this problem from a computational point of view. We need to be able to deduct the interference pattern from the entire signal so that we can draw nice maps from it. Honestly, with a 1.2 meter dish, you can't expect too much, but it's a nice proof of principle. And then there is always the possibility, like the VIRAC guys told us yesterday, to go into what we call VLBI connections, where you connect telescopes, large telescopes that are spread out halfway across the globe, but you do essentially the same style of measurement. We also want to do this, we're also preparing for this, but this is still a bit of time away. We need to invest some more work there. Okay, so I've always talked about what we are doing at Stockert. I thought it might be interesting to give a short overview of what all the others out there are doing and whom we know and who we collaborate with. This is a short overview of the stations in our more or less immediate vicinity. Stockert itself is here, south of Bonn. And well, starting from the north of Germany, south of Kiel, there is a very interesting project, a private station, DL0SHF. Some guy has several satellite dishes spread out in his backyard. I'm also working with him. And he's doing, amongst other things, data taking for NASA for the stereo satellites. You may know this project. The stereo satellites are positioned. Suppose this is the Earth trajectory. Earth is here. Then the stereo satellites are positioned here and observing the sun from two angles. And he's taking low data rate data that NASA itself is no longer able to take. The next one to the south is the Dutch station in Dwingelo. They have a historic 25-meter dish that was built in the same time as ours, and they are also connected to the adjacent interferometer by the Dutch radio astronomy organization Astron. They are doing classical radio astronomy on their instrument and have had it beautifully restored only recently, so that's essentially a new dish currently. In Bochum, in the Ruhrgebiet, there is a large radome. By the way, if you've never seen a radome, that's actually quite interesting. The idea is, if you want to protect antennas from the weather, you can not really create a classical dome or hall above them, because every thick material and every steel girder will make it impassable for radio waves. So what you do is you create a large so-called, that's something difficult to translate, a Traglufthalle. So essentially you blow air under pressure under a large canvas that forms a protective shell around the telescope. That's what you're seeing in all these reports currently going through the news from the Bad Aibling station. In Bochum, such a radome houses a 20-meter dish, and they're doing a lot of museum work. They are mainly playing on the fact that they were the first Western station to receive Sputnik when it was launched. And they're also doing a lot of satellite work. They are the main control station for the German amateur satellite community. Then next to the south, we have two commercial or professional instruments that we are working together with. One is the Fraunhofer FHR radar in Wachtberg. The radar system itself is called TIRA. Below that radome, they have a 30-meter dish that can send out active radar at, amongst other frequencies, this 1.3 gigahertz where our receiver is optimized for. A very powerful instrument used for this detection of space debris. And then, of course, in Effelsberg, there's the 100-meter dish, the largest steerable telescope in Europe, and depending on how you count it, the world. They've got this 100-meter dish, and by the way, what's also interesting, they've got a LOFAR array down there. That is a new development in radio astronomy where they want to look at very low frequencies, and these antennas are just bricks of styrofoam coated with a black foil, and then you spread them out over a normal field. Or the other design is a stick put in a field across a 1 square meter construction steel sheet, so just the stuff that goes into reinforced concrete walls, 2 wires across it, and that's it. Dozens of them across a field. All the signals go directly into an AD converter and then into a supercomputer. And that means you've got an array where you can, just by using a computer, have many virtual beams at once looking in the sky. That is one interesting thing, so you can observe several sources at once. The other thing is they're always hoping to sort of store their data in a ring buffer so that say a supernova explodes somewhere, you can go back in that ring buffer and look at that location in the sky like it was 10 hours ago and see the explosion unfold in real time. That is not a reality yet, but yeah, just as a side note, that's a very interesting project. And the southernmost station in Germany is Reisting. The radome in Reisting was the first German satellite uplink station. There's a 25-meter dish under a radome, and it's still being renovated. They are still working on recommissioning it, and the aim, Max, I hope that's correct, are mainly satellites and control work for amateur satellite groups, right? So. Okay, other things that did not fit on our map. We've heard the presentation of Virak from Ventspils only yesterday, so you already know what that project is about. Then we had some preliminary contacts with the Deep Space Exploration Society in Boulder, Colorado, who have two, well, depending on what they can use, 2 to 3 satellite tracking dishes, old dishes from NASA. This has gotten a bit difficult because of international relations. Americans are no longer expected to export knowledge about satellite control. And then they had an internal problem where they lost one of their dishes and got an identical one. Only problem was the first one, which they lost, they just had completely renovated. And when it was back to working order and in perfect condition, NASA said, oh, hey, by the way, we need that again. You can have that one. You know how to restore them, right? Was a bit of a pity. So yeah, that has gone not so well so far. So if you are interested in that or know anybody, we will host a conference at Stockert called EUCARA, the first European conference on amateur radio astronomy, hoping to get the entire, at least European community together in early September. And yeah, we'll have to see what we can do, perhaps look at some interesting projects where we can work together and see how these things turn out. Now, I've been talking a lot about all the work involved, and as you can imagine, restoring such a large telescope for many years is not without its drawbacks. And it's a whole lot of hard work. I mean, we've spent essentially 2 years just down in the cellar doing invisible work, rewiring everything. So yeah, it's always a bit the question, why are we doing this? Where's the point? What makes it so interesting? And apart from the fact that it's just technologically very interesting and rewarding, and that it's cool to always push the frontier of what you're doing yourself and what you know that your telescope can do. It's also just simply that it's a cool place out there, and when you're alone there at night, you can always go to the 10-meter dish, grab control, point it to the moon, send a few Morse dots out there, and after 3 seconds you get your signal reflected from the moon's surface. And what you send out as very clear, very precise Morse dots comes back frequency shifted because of the moon's relative motion, distorted and widened by passing twice through the Van Allen belts, and of course very weak by the sheer distance, and because the moon is of course not a perfect reflector. And so when you get back these very weak, very distorted reflections after 3 seconds, that really gives you a feeling for the dimensions in space. I mean, the moon is our next neighbor, and it's 1.5 light seconds away. So that's one of the very few possibilities where you can really feel distance. And then, of course, you can look past the moon to all these stars that we're measuring and try to imagine these dimensions. And that's normally the time when you should resort to mathematics, because then things get strange. Okay, thanks a lot so far. That was essentially the tour through Stockert. If you have any more questions, let's get them right now, or just meet me outside in the hall or next to our poster. Thanks a lot for your attention.
Okay, thank you very much, Juergen. And if there are questions, just raise your hand and I will come with the microphone.
You have mentioned several open source tools. Mm-hmm. At least it was something about GNU Radio project. Mm-hmm. And it seems to me that I have noticed some plots done in GNUplot, mm-hmm. maybe. Can you tell several words about the open source software which is used? Mm-hmm.
Mm-hmm. Sure. We're essentially using almost exclusively open source software. Our complete control system runs on Linux. The control program itself is written in Python. The analysis software that we're using is called SIGPROC, which is a rather old package, also by Duncan Lorimer. It's written in Fortran, I don't know if it's 77 or Fortran 4, something not quite recent, and C. The only thing where we're using closed source software is everything related to the FPGA spectrometer, because there, of course, the cores have proprietary parts and the control program is written in LabVIEW. It runs on Linux, but it's, of course, not open source. Apart from that, as you noticed, yeah, we're using all standard Unix plotting tools like GNUplot, GNU-R. And on the hardware side, it's a bit more tricky because, yes, as you said, the USRP is a GNU Radio peripheral, but most other things where it comes to machine control are still very much Windows-oriented, especially software-defined radios can usually only be read from Windows. But apart from that, all the core components of the system are Linux only. Sorry, microphone? Sorry.
And what about the usage of GNU Radio in compared with some maybe proprietary analogs, for example?
I'm afraid I'm not, I don't know very much about these experiments compared to other SDRs. So what we're doing in general is use software-defined radios as simple spectrometers for special purposes because they can be easier to program in some cases. But I don't know about, for example, a noise figure comparison between USRP and others. We're also using commercial software-defined radios. What I can say is that this RTL SDR, the simple USB TV stick, is sufficient for very simple purposes, but of course has a really bad noise figure.
Okay, are there any more questions? Okay.
So could you say a couple more words on what you presented as the distribution, studying the distribution of matter in the galaxy through Doppler shift? How do you convert a velocity into a distance, I guess?
Yes, I will just have to, sorry, I didn't have that open. Okay, so in general, the Doppler shift and frequency are directly proportionate. The problem is that in the galaxy, we are not occupying the outermost position or the innermost position of orbits, but we're somewhere in between. So that means that if we measure any velocity, we need to cross-check this observation and see if it's orbiting far more in the outside or more in the inside. Because a cloud that is appearing to move towards you can either overtake you on a more innermost trajectory, or it can actually move towards you. That's what these high-velocity clouds are. After you've figured that out and taken the local standard of rest correction, you would try to arrange the clouds in an area along your axis of sight, and would, for the individual clouds, calculate the speeds. As I said, essentially I would have prepared this, but I can't find the slide now at the moment. If you're wanting to go into more detail, we can take this offline.
Okay, thanks.
Okay, any more questions? Pardon?
Yeah, okay, I can just repeat the question. I think it was if there were any other people working on interferometry, is that right?
Yes, the influences.
I'm aware of several small-scale university experiments at different universities, but I'm not certain if there are any amateurs in the world that do VLBI. At least Ventspils and ourselves are very interested in that. Also, the guys from Boulder have expressed interest, but I'm not aware of any working collaborations. The thing is, VLBI has a few challenges. For example, you need to synchronize times across these observatories very precisely, and you get a lot of data out of it. We've seen on yesterday's presentation the data recording devices that they have. So essentially, you don't transfer the data over the wire, you ship hard drives because it's faster. And then, of course, VLBI is a field where all the professional observatories are already active. So apart from personal curiosity, it is not quite clear what two, let's say, 25-meter dishes in suboptimal positions with perhaps over the years deformed surfaces can contribute to the field when there's two 100-meter dishes collaborating at the same time.
Okay, if that's all questions, I have one question though. My question is for private people from outside your Astropeiler. Is there any possibility to contribute or get data from you or something?
Yes, actually, everything's possible there. Our data is freely available to everybody who wants to work on it. Just contact us. And if you want to contribute, we are always looking, or know somebody who wants, we are always looking for volunteers. That's actually our largest problem at the moment. We need essentially every skill, starting from masonry and woodwork over electrical engineering, computer programming to FPGA programming. The thing is, we are not a very online organization. So it might be a bit tricky getting the collaboration flowing at first, but I'm sure we could figure something out. If anyone wants to do a joint measurement project or just wants to visit, contact us. Our email address is just simply info@astropeiler.de. And if you want some measurements done to any specification, also contact us and we'll see what's possible.
Okay, thanks a lot, Juergen, for your talk. Just get your applause from the public.
Cool. Yeah, thanks a lot.